Hello, welcome back to the second video in the AP Computer Science Principle series. Today we're going to go over decimal. So another name for decimal is denary. Denary is a more commonly used term in places like the UK, anywhere that uses the British curriculum. For if you're American, you'll use the term decimal. So to convert from denary, aka decimal, to binary, last class we learned about binary to decimal. So this time we'll learn about decimal to binary. There are two methods that I will teach you. They're both very easy. One is called, or well, I call it the subtraction method. Another one, I call it the division method. And you'll see why. They're very self-explanatory names. So let's begin with the subtraction method. Take any decimal number, denary number. For example, 67. Then look at this chart. Feel free to screenshot this, pause here, write it down, or print this out. Step one is starting from the left, ask yourself, what is the largest number you can subtract from 67 without going to the negatives? Well, 67 minus 128. Is that negative? Yes, it is. So we put a 0 here. Next, look at this number. Can we subtract 64 from 67 without going negative? Yes, we can. So we put a 1 here. Then we do 67 minus 64, which gives us 3. Right? What's our new number to work with? It's 3. So 3, what's the next number here? 32. 3 minus 32. Does that go into the negatives? Yes, it does. So we put a 0 here. 16. So 3 minus 16. Does that go into the negatives? Yes, it does. Put a 0 here. Next one after that is 8. 3 minus 8. Does that go into the negatives? Again, yes. So 0. Next, 3 minus 4 for this one. Does that go into the negatives? Yes, it does. So again, a 0. Now, the next number is 2. Aha, things get fun. 3 minus 2. Does that go into the negatives? No, it doesn't. So we can put a 1 here. What's our new number to work with? It's 1. So now we take 1. What's the last number here? Yep, it's 1. So 1 minus 1 is equal to 0. We put a 1 here, and we're done. So 67 in binary is 0, 1, 0, 0, 0, 0, 1, 1. Well, in 8-bit binary. Right? So this is this is what I wrote. This is what I just explained, right? So again, 67 in binary is 0, 1, 0, 0, 0, 0, 1, 1. Let's try another one. So in a live class, I would have students give me a number. Since we're doing a recorded class, I'll just make up the number. How about 113? No reason, I just made that up. So 113 minus, what's the first one here? 128. That goes into the negatives. So 0. How about 113 minus the next one? 64. Ah, that works. So that gives you 1. What is 113 minus 64? It's 49. Do you need a moment to use a calculator? So anyway, it's 49. What's our new number to work with? 49. So by the way, feel free to use a calculator if you want. Now, the next number is 32. So 49 minus 32. Can we do that without going into the negatives? Yes, we can. So we put a 1 here. This is 17. So the new number to work with is 17. Now, what's the next one here? 16. 17 minus 16. Can we do that without going into the negatives? Yes, we can. So we put a 1 here. Our new number to work with is 1. So we take this 1 and we look at this 8. 1 minus 8. Can we do that? No, we can't. It becomes negative, so 0. After that is 4. So 1 minus 4 gives you something negative, so can't do that one. How about 2? 1 minus 2, that's also negative, so we put a 0 here. Finally, we have a 1. 1 minus 1, that works. Gives you 0. So 113 in binary is 0, 1, 1, 1, 0, 0, 0, 1. Your turn, so do this on your own. You can, yes, you can pause this video and convert these to binary on your own. Go. So I guess you're finished pausing. Let's check your answers. 0, 0, 0, 1, 1, 1, 1, 1. Second one is 0, 0, 1, 1, 0, 1, 1, 1. Next one is 0, 1, 0, 0, 0, 1, 1, 0. Finally, we have 0, 1, 1, 0, 0, 1, 0, 1. How many did you get right? Did you got them all right? If so, give yourselves a pat on the back. So, what are some advantages and disadvantages of this method? Well, for starters, it's very, very easy, right? And it's quite quick to do. But what are some disadvantages? Well, I can think of one. It's tedious for very large numbers, and I don't know about you, but this would be very hard for me to do without a chart right in front of me. So that leads me to the other one, division method. So before we get into the division method, I need to tell you about two terms, LSB and MSB. So if you look here, this one, the position it's in is very important. This is called weighted positional representation. Weighted positional representation. Okay? So just like, for example, if we had a number like 159, well, normally 9 is greater than 1, right? But in this case, no. This 9 is just a 9. This 1 represents 100. So this 1 is greater than this 9 because this is actually a 100. Similarly, this 1 represents a greater value than this 1. This one just represents 1. This one represents a 2. So this one here that I circled is called the LSB. What does that stand for? It stands for least significant bit. Okay? LSB, least significant bit. Now, if that's the LSB, what do you think this one is? That's right, it's the MSB. So if LSB stands for least significant bit, what does MSB stand for? Most significant bit. That's right. So let's delve into the division method. Step 1, take any denary number, aka decimal number, divide it by 2. So let's take 88, for example. I'm going to write it manually. So 88. And then we're going to divide by 2, which gives us what? Gives us 44. Quite easy. What's the remainder? 0. What's the new number to work with? 44. So now I'll take this 44, divide it by 2, gives us what? 22, right? With a remainder of 0, right? Now, we keep going. The new number to work with is 22. So 22 divided by 2 gives you 11. Again, with a remainder of 0. What's our new number to work with? 11. Now we take 11 divided by 2. It gives us, so what's the nearest integer rounded down? It'll give us 5 with a remainder of 1. The new number to work with is 5. 5 divided by 2 gives us 2. Okay? With a remainder of 1. Now, 2 divided by 2 gives you 1. With a remainder of 0. What's the new number to work with? 1. 1 divided by 2, rounded down to the nearest integer is 0, with a remainder of 1. Once you reach 0 here, you are done. So this is 88 in binary, but be careful. Many students get it the opposite order. So this is actually the MSB, and this is the LSB. If that's the case, what is 88 in binary? It is 1, 0, 1, 1, 0, 0, 0. Okay? Notice how many bits are here? 7 bits. I generally prefer having binary numbers in multiples of 8, just because 8 bits makes 1 byte. If there are 7 bits, it's easy to do. Just add one leading 0 at the beginning. So this is called a leading 0. Right? Leading 0. So this is just the written explanation of what I just did. So 0, 1, 0, 1, 1, 0, 0, 0. Right. So let's try another one together. Since this is a pre-recorded class, normally I just ask students to shout one out. But since this is pre-recorded, I'll just make a one up myself. Let's do a fun one. 125. That's pretty fun, right? So 125 divided by 2 gives you what? 62 with a remainder of 1. So the new number is 62. 62 divided by 2 gives you 31 with a remainder of 0. The new number to work with is 31. 31 divided by 2 gives you 15 with a remainder of 1. What's the new number to work with? It's 15. So 15 divided by 2 gives you 7 with a remainder of 1. What's our new number to work with? 7. 7 divided by 2 gives you 3 with a remainder of 1. What's our new number to work with? 3. So 3 divided by 2 gives us 1 with a remainder of 1. So 1's our last number. 1 divided by 2 gives us, rounded down to the nearest integer, is 0 with a remainder of 1. Once you get to 0 here, you are done. And there we have it. Remember, this is the MSB, and this is the LSB. So 125 in binary is 1, 1, 1, 1, 1, 0, 1. So 1, 2, 3, 4, 5, 6, 7. So since this is 7 bits, what can we do? If we want to make it 8 bits, yes, that's right, just add a leading 0. All good? So what are some advantages and disadvantages of this method? Well, I can tell you one major advantage. You can use it for very, very large numbers, even if you don't have a chart in front of you. Your turn. So pause this video, pause, use the division method to find the binary representation of the following decimal numbers. Go. Okay, now that you can come, no. So I imagine you pause the video and come back. The answers are 1, 0, 1, 0, 0, 1, 1, 0. 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, and those are the answers. Okay? Right. So next, some practical implications or questions that are likely to appear on the AP Computer Science Principles exam. Well, so some concepts that are tested on the AP Computer Science Principles exam. For some reason, you want to message your friend using binary code. Now, I don't recommend you do this in real life. You might lose a few friends. So on the next screen, use the subtraction method for the first 5 characters and the division method for the last 5 characters. Remember, spaces and punctuation are characters too. And remember that capital and lowercase letters are different. Also remember, if you figured out one character one time, you don't need to figure it out again. It's the same binary code. So imagine you have a friend who texts you, or imagine you want to send a friend this message. Where are you? Remember that the space and the question mark are also characters. How do you do this? Well, you can look at your ASCII table, find the corresponding decimal numbers for capital W, lowercase h, lowercase e, lowercase r, space, letter U, question mark. Turns out it's these ones. I'll save you the effort of looking in your ASCII table. So now, use the subtraction method here and the division method here. Go ahead and pause this video and come back when you're done. Done? All right. So here you have it. The text message where space r space u question mark in binary is this. Next topic is this. Can you read here? This is called bit capacity. First, let's do some basic math review. So this is probably around middle school math level. 2 to the 10th power divided by 2 to the 6th power is 2 to the 4th power. 2 to the 8th power divided by 2 to the 5th power is 2 to the 3rd power. 2 to the 24th power divided by 2 to the 10th power is 2 to the 14th power. So you all know how to do those? Perfect. If you don't, I recommend you go somewhere and practice exponents. So let's go here. These are the answers. 2 to the 4th, 2 to the 3rd, and 2 to the 14th, which is exactly what we wrote. Question. If you have one bit, how many different outcomes are possible? The answer is 2, either 0 or 1. So if you have two students and you want to give each student a unique ID number, is one bit enough? What do you think? Yes or no? Well, the answer is yes. The first student can be 0, the second student can be 1. But what if you have three students? Is one bit enough? No, it's not. So the first student, you would need at least 2 bits. So the first student with 1 bit would be 0, second student would be 1, but what about the third student? To do so, you would need at least 2 bits. Student 1, 0, 0, student 2 is 0, 1, student 3 is 1, 0. New question. Well, not question. Actually, 2 bits is enough for 4 students to each have their own unique ID. This person here is a 0, 0, this person is 0, 1, this person is 1, 0, and this person is 1, 1 as their ID numbers. All good so far? But what if you have 5 students? Is 2 bits enough to give each one a unique ID number? No. You would need at least 3 bits. Did you notice the pattern? If you have m unique objects, you need n bits such that 2 to the nth power is greater than or equal to m. So thus, if you have 3 bits, how many different objects can you represent? That's right. You can represent a maximum of 8 different items. Some practice questions for you. Imagine this. A mobile game allows players to collect between 0 and 500 coins. You want to store a player's coin count using the fewest number of bits possible. What is the minimum number of bits required? Go ahead, pause this video to figure it out. So there are between 0 and 500 coins, which means that we need at least 501. Why? Because 0 is the first one. That means 2 to the nth power must be greater than or equal to 501. So what's the answer? The answer is 9 bits. Go ahead, figure out on your calculator what 2 to the 9th power is. Question 2. A website allows users to rate products on a scale of 1 to 100. You want to store these ratings using the smallest data type possible. What is the minimum number of bits required to store a rating? So how many different possibilities are there this time? That's right, 100. We don't start from 0. So we want 2 to the nth power to be greater than or equal to 100. Any ideas? Go ahead, pause this video to figure it out. 7 bits. All right. Now look here. A video streaming website uses 32-bit integers to count the number of times each video has been played. In anticipation of some videos being played more times than can be represented with 32 bits, The website is planning to change the 64-bit integers for the counter. Which of the following best describes the result of using 64-bit integers instead of 32-bit integers? Remember, originally we could store 2 to the 32 power different things. Well, now if you store 2 to the 64th power, how many times more things can be represented? That's right, 2 to the 32nd power more can be represented. The answer is C. Oh, are there two? It says question 3 twice. I'll change that in I'll change that in the future. So this should be question 4. Anyway, an online video website records the number of likes each video receives. At first, when the website was still new, it stored likes using 16 bits. However, as the website became more popular, 16 bits was not enough, and the website switched to 24 bits. How many more values can be represented with 24 bits than 16 bits? Go ahead, feel free to pause the video to figure it out. Basically, 2 to the 24 divided by 2 to the 16th gives you 2 to the 8th, which is B. So that's the end of our class today. Thank you very much for watching, and I'll see you again soon. Take care.